All right, guys, and we are finally into the last portion that we're going to handle here of section 3.8. So we're calling this E, and it's on equations of parallel and perpendicular lines. This one section is really the reason that we cover section 3.8 at all, because if you recall a million years ago, we were talking about parallel and perpendicular lines in chapter 3. We were really focusing on what happens when you have two lines cut by a transversal and all of the different angle pairs that you had there. And very often, those two lines that we had were parallel to each other. And anyway, that's kind of the point of what we're doing here in chapter 3. So let's get rid of that junk right there, and let's focus on the first major idea, the first of two major ideas that we have here within this section. Parallel lines have equal slopes. I've seen some geometry books before where this is actually a separate theorem, but for now your authors in your textbook just kind of state this as a fact that we should know. Parallel lines, in order for two lines to be parallel, they've got to have slopes that are exactly the same. Now I'll come back to this statement here in just a second. So to prove this, if we were in class, I would have somebody just randomly shout out a slope and randomly shout out a y-intercept. So I guess I'll just do that myself. The slope I'm going to come up with here is maybe negative 2 over 3. I'll put an x after that. And then how about we go with something like a plus 4 for our y-intercept. So just making up a particular equation right here. This one is in slope-intercept form. And if we wanted to graph it in the coordinate plane that we have provided here, we would first deal with our y-intercept of 4, meaning from the origin, we would go up 4 units and put a dot right there. Then we would focus on our slope of negative 2/3. So from that y-intercept, we would travel down 2 units and then right 3 units and get another point on our line. I might do that again. Down 2 and right 3, there's yet another point right there. And if I ran out of room, I might reverse that and rather go up 2 and left 3, and there you go. So those 4 points are probably good enough for our purposes here. We would now draw the one and only line that passes through those 4 collinear points, and that would be the line y equals negative 2/3 x plus 4. Now what I would do is ask somebody else to give me another line right here, but I kind of want to prove, or at least experiment with, this idea right here, that parallel lines have to have equal slopes. So the slope of this new line that I'm about to do in purple is going to have to be equal to the slope of the line we just did in blue. So we'll still have a y equals negative 2/3 x, but now we'll pick a different y-intercept. How about negative 1 for this one? So if we were graphing that purple line, we'd use our y-intercept of negative 1, so down 1 unit from the origin, and then again follow the slope of negative 2/3, which tells me to go down 2 and 3 units to the right from the point where we started. Let's do it again. Down 2 and 3 to the right, or we could reverse and go up 2, left 3. Up 2, left 3, and so on and so forth. So now we'll go ahead and we will connect those collinear points with a hopefully straight line that looks like that. And what I'm hoping you guys would see by looking at this right here is that these two lines, both having the slope of negative 2/3, do in fact look parallel to each other. In fact, if I cheated and just pulled the blue line over there on top of the purple, okay, I didn't draw it great, but you guys can see that those are close enough to being parallel to each other for government work, as they say. So maybe I'd go ahead and put the arrow in the middle of this line and the middle of this line, and that kind of supports this idea here, guys. Parallel lines have equal slopes. Now, the one thing I said I would come back to is this concept right here. All vertical lines are parallel. That's one that people usually look at and go, okay, that's obvious. Why is he pointing that out? Like, for example, if I were to draw a vertical line over here, that has an x-intercept of negative 8, so this is the line x equals negative 8. And then if I were to go, I don't know, maybe over here somewhere and draw the one and only vertical line right there, that one looks like it has an x-intercept of 4, so this would be the line x equals 4. And it's not really hard to see, guys, when you look at a graph, that these two vertical lines are parallel to each other. So I'll put a double arrow on each of those. The real question, I think, is why did we take the time to actually write this out? Isn't this statement right here sufficient? Why did we need this? Well, here's really the kicker, guys. You need that second part to the statement because, let me switch colors on you here to green for just a second. One of the things we hopefully remember that we talked about at the beginning of section 3.8a when we did slope, but also 3.8d, is that in every vertical line, the slope is undefined. That is true for this vertical line here, and then also this one on the right. Slope is undefined. And if two lines have undefined slopes, you can't say that their slopes are equal because their slopes don't exist. So equal really means having the same value. And if these slopes are undefined, they don't have values at all in order for them to be equal to each other. So honestly, this is one of those statements right here that I think if a math teacher didn't say it, everybody would understand the concept here that vertical lines are parallel, but technically this statement on top doesn't apply to vertical lines, so we need this second one. Okay, let's see this concept in action, guys. What we're going to do now is do a problem that should feel very similar to the ones that we did back in section 3.8d, where we were given a certain amount of information about our line, and we had to come up with its equation. And one of the things I keep meaning to fix here in my directions, guys, we're going to find the SIF equation of this line. Slope-intercept form is where our answer needs to be. So we're trying to come up with the equation of a line that is parallel to this line right here, and that also contains the point 2, -3. Here's what we need to focus on, guys. This line that they gave us right here, that's not our answer. We need a line that's parallel to that. So the first thing we should probably do is recognize that this equation was given to us in slope-intercept form. So it should be really easy to see that the slope of this line is -3. It's just the coefficient of your x if you're in slope-intercept form. And now the little notation that I like to use here, guys, is this. An m with that symbol right after it as a subscript. And I write that to mean the slope of a parallel line. So if the line they gave us had a slope of -3, what would be the slope of a line parallel to that? Well, let's go back to this concept right over here. Parallel lines have equal slopes. So the slope of any line parallel to this would also have to be -3. Now that seems simplistic. It'll get more complicated when we get to the second half of these notes. So right now, you guys, we know the slope of our line, and we also know a point that it passes through. Let me say that again, but backwards. We know a point on our line, and we know the slope. So if we know a point and the slope, we are going to go to, you guessed it, point, there we go, point slope form. You're going to use point slope anytime you know a point and the slope, and that's where we are right now. So point slope form is going to be y minus your y coordinate of -3. Well, subtracting -3 is the same as adding 3. That equals our slope comes next, which is -3, and then in parentheses it's going to be x minus your x coordinate of 2. Now there's the equation in point slope form, but you'll notice the directions asked for it in slope-intercept. One of the main concepts you guys need to get right here that even good Algebra 2 and pre-calc and even calculus students don't always get is that point slope form and slope-intercept form aren't two completely different things. They're related to one another. So if we want to get from point slope into slope-intercept, what we need to do right now, guys, is solve for y. We need to get this y all by itself, and the first step to that is distributing our slope, the -3. So y plus 3 equals -3x plus 6, and then all we have to do is subtract a 3 from both sides, and this should get us our final answer. Y equals -3x, and plus 6 minus 3 is going to be plus 3. Now I think that's the answer. But let's go back and let's check what it needed to do to find out if we're right. First of all, we needed a line that was parallel to this line right over here. Well, the slope of this line was -3, and the slope of our line is -3 as well. That tells me they're parallel. The trickier part is making sure that this line we just came up with contains the point 2, negative 3. So to do that, guys, what we're going to do is substitute this value in here for x and this value in here for y. So my y value would be negative 3, and that should equal a slope of negative 3 times an x value of 2 plus 3 at the end of all that. I don't know if this is right. Let's check it. Negative 3 equals negative 3 times 2 is negative 6. Negative 6 plus 3 is negative 3. There's the true statement we were looking for, and that is our correct answer then. And guys, if we wanted to take the time, I provided the graph here so that we could graph both the original line and this new line right here. I guess we can do that real quick, and let's see what we got. The original line, our y-intercept is negative 2. Our slope is negative 3, which is down 3, right 1, or up 3, left 1, up 3, left 1. Okay, here's the original line, not very straight, but right there. Our new line has a y-intercept of 3 and a slope of negative 3. Down 3, right 1, down 3, right 1, down 3, right 1, up 3, left 1. Okay, and here's the second line that we just came up with. And two things better happen. First of all, are those two lines parallel? Definitely looks like they are. And finally here, let me switch to purple, does our second line contain the point 2, negative 3? 2 to the right, 3 units down. There's 2, negative 3, and the graph kind of supports the idea as well. Now, frankly, guys, if it were me, I wouldn't waste my time with the graph. This work here in green is really what you need in order to check yourself. But regardless, yeah, we got this one right. Go us. Let's take a look at example B. Now, this one reads a lot like the one that we just did, but it's got one fundamental difference that maybe you'll see right off the bat. If you go back and look at that last example, boy, I wrote a lot of junk over here. The first thing we did is talked about the slope of the original line, and it was just negative 3. So now I'd ask you guys right now, again, we're trying to come up with the equation of a line parallel to this one right here. I would ask you guys, what is the slope of that line? But unfortunately, this question is a lot more complicated than when we asked it back in example A, because in example A, the line given to you was in slope-intercept form. Here, it's not. Now, depending on how much your teacher talked about this, guys, that equation is in something called standard form, where the x and the y are on the same side of the equal sign, and a constant is over there on the right. Now, personally, I don't spend a whole lot of time discussing what standard form is when we're talking in geometry here, guys, because I don't care that much. Most of you guys know that if you want to deal with that line, you probably want to get it into slope-intercept form. So we're going to solve this equation here for y. First step, minus 2x from both sides here, and that is going to give us a negative 3y is equal to, probably better to write this as a negative 2x plus 12. Then from there, we'll divide all three terms by negative 3, which was our coefficient of y, and we're going to get y equals negative 2 divided by negative 3. Well, negative divided by negative is a positive, and what's 2 divided by 3? Guys, the answer is staring you in the face right there. It's 2/3. This is the reason fractions were invented, because sometimes division problems don't have a nice answer, so we just say 2/3. The x tags along, and then we've got a minus 4 at the end of all that. Okay, so now we've taken this line and we've written it in slope-intercept form. So now you guys ought to be able to tell me what is the slope of the original line. That's going to be 2/3. And then from there, what's the slope of a line parallel to that? Well, parallel lines have equal slopes. So this slope is going to be 2/3 as well. So we now know the slope of this line, and we already knew a point on this line. So since we've been given a point and we found the slope, we are once again going to go to point-slope form. So here it is, everybody. Y minus your y coordinate of 5 equals your slope, which is the fraction 2/3, times in parentheses x minus your x coordinate of 9. Now, that's point slope. To get it into slope intercept, yet again, we're going to solve for y first by distributing here. So y minus 5 is equal to 2/3 times x is just 2/3 x. And now this is going to be a minus. And hey, here's a magic trick, guys, for how to multiply a fraction times a whole number. Start with the whole number, 9, divide it by the number on the bottom, multiply it by the number on the top. That's what's going on here, guys. So 9 divided by 3 is 3. 3 times 2 is 6. You're going to be able to use your calculator here, but that's a way you can be a little bit less dependent on it. Last move here, guys. Let's add a 5 on both sides. Those cancel. And we're going to get y is equal to, we now have a 2/3 x, and minus 6 plus 5 is minus 1. So there's our answer. Let's just double check it real quick, guys, to make sure that 9/5 works when we plug it in here. So what goes on here? Our y value is going to be 5. That should equal 2/3 times an x value of 9 minus 1. So 5 equals, we just did this trick here, guys. 2/3 of 9 is going to be 6, and 6 minus 1 is 5. Check. I feel good about that answer right there. Okay, so B was a little bit harder than A because the equation we were given was in standard form instead of slope-intercept. So what did we do? We took this standard form equation and we got it into slope-intercept form, and then we were able to read the slope. Okay, one more example in this part of the notes, guys. Similar problem. Find the equation of a line. This is parallel yet again now to x equals 6 that contains the point -7, 3. Now, I'm hoping you guys recognize that something is different about this problem than the last two. The line we were given is x equals 6, and that line right there is kind of funny looking because it doesn't contain a y. All it has in it is x equals a constant. So I would ask you guys, what kind of line is that? Anytime it's just x equals a number, that is a vertical line. And I know it's silly, but I always remember that because when you have x equals, there's a little v sitting right on the top, and there's your vertical. Now, the line that they gave us was vertical. Therefore, a line parallel to a vertical line is going to be, let's go back to something we wrote earlier right here, all vertical lines are parallel to each other. So that means that our parallel line is going to be vertical as well. So we've got a vertical parallel line. And again, now let's keep the thought process going. What's the equation of every vertical line? It's going to be x equals some value right here. And that value, we called it A in our notes in 3.8D, that value is the x-coordinate of any and every point on that line. Now, we know that our line has to pass through the point -7, 3. So what is the x-coordinate of that point? -7. We are done with this problem, guys. That is all you needed to do. We needed to recognize that the original line they gave us was vertical, that anything parallel to a vertical line has to be another vertical line, that the equation of every vertical line is x equals a constant, and the constant was just the x value here of that point, which was -7. So I said this before, I'll continue to say it. Horizontal and vertical lines are much easier to work with than the diagonal lines that we dealt with here in example B and example A. And yet, people do worse with these problems because they didn't memorize that table properly at the beginning of 3.8D. So guys, go back and look at that table again. It's really going to help you with problems like this. Okay, this is a great spot for me to stop this video right here, and then I'm going to pick up a second video with the second half of this section of notes. So all of that was on parallel lines. The next video is going to get into perpendicular lines. We'll be right back.